Hello, everyone. So here we have in our session, I will start by, okay, I'm sorry, guys. Oh, so, hi, guys. Sorry, I thought, so let's start with our spotlight research, our main session and our amazing session. So as we move to the heart of our summit, I'm really honored to introduce to you our spotlight speakers, distinguished by individuals who has work not only contributed significantly to the field of artificial intelligence, but it has also paved the way for future innovations. Today, they will share with you their insights and their amazing work that has contributed significantly to the world of AI and their research has also uh, paved the way for future innovation, right? So today they will share with us their insight and challenges and opportunities that lie ahead of our quest to harness the full potential of artificial general intelligence. And firstly, I would like to introduce to you our distinguished speakers from the Spotlight Research. And we will have on first the amazing Steve Phillip, where he will be taking us through his research, where it's talking about investigating emergent goals like behavior in large language models using experimental economics. And Steve Phillip, the stage is all yours now to present your research.
Thank you very much.
Thank you.
So I will share my screen. 1 second. Good. Welcome, everybody. I'm Steve Phelps. I'm going to be talking about AI safety from the perspective of an economist and a behavioral psychologist. So this is a collaboration with Van Russell and Rebecca Ranson. Van Russell at Middlesex University and Rebecca Ranson at University of Essex. We have a number of papers. We have several papers, some of them in submission on AI safety using experimental economics. You can find out more at the our GitHub repo. So I'm going to talk about AI alignment, AI safety, and I'm going to talk about human safety. So when we talk about human safety, we talk about social dilemmas, and trust and reciprocity. So I'll talk about how humans build trust, and then I'll talk about how we can establish whether large language models can build trust using similar concepts. And I'll focus on a very famous example called the prisoner's dilemma. So in the classical AI alignment problem, we have a one-to-one correspondence between a human designer and an artificial agent. And the human designer attempts to ensure that the agent has the correct utility function, that it's a safe utility function. And we typically do so by a training process. So in the case of ChatGPT, OpenAI is a designer and they train ChatGPT using reinforcement learning from human feedback. So this is a little bit strange if you think about it, because in real life there are lots of humans and they're not aligned with each other. So human society has lots of agents in it and we're not always aligned, and sometimes we have conflict. And the way that humans resolve conflict is not by training each other so that we all want the same thing and behave the same way. So there are examples of that in history, but they typically haven't ended well. There's eugenics, for example. And what we're trying to do is see whether some of the concepts that humans use to ensure that human society is safe also can be applied to large language models. So humans typically ensure that society is safe by establishing trust. So we've got lots of different people, they've got lots of different utility functions, lots of different goals. And when we meet other people, we don't try to align them by changing their utility function with some kind of magic ray. Instead, we acknowledge that we have different utility functions and we attempt to build trust. How do we build trust? We see what other people do And if they're nasty, we don't reward them. So when we're interacting with each other, with other people, we watch and see what they do. Remember, this is called direct reciprocity. Or if we notice that somebody is behaving badly towards others, we might tell other people about that. And that's reciprocity, indirect reciprocity through reputation. And the idea is that this creates incentives for agents to act nicely. We don't force agents to act nicely, we create incentives for them to act nicely. And what we're trying to do is see whether large language models, in a sense, understand these concepts. So the way that we do this is by using experiments. And these experiments are experiments that have been done with real people. And what we do is we create a very stylized task that establishes the conditions for trust. So a very famous example is a game called The Prisoner's Dilemma. In the simplest version of the game, you have two players. They both have to choose simultaneously between two different choices, whether to be nice or whether to be nasty. The nice choice is typically labeled cooperation, C. The nasty choice is labeled D for defection, and it's called Prisoner's Dilemma because in the way that it was originally formulated, we imagine two prisoners have been arrested, and if they keep quiet, if they both keep quiet, this is the keeping quiet is the cooperate action, then they both go to prison for 5 years. But they can also choose to defect by reporting the other prisoner's crimes. And if they do this, the prisoner who rats on the other one gets 1 year if the other prisoner cooperates, and the prisoner who kept silent in that situation goes to prison for 10 years. If both prisoners rat on each other, they only go to prison for 8 years. And typically, rather than minimize time in jail in a experimental economic setting, we try to set it up so that we're maximizing some kind of monetary payoff, which is why I've written the payoffs in dollars. So here, the first player gets $5, the second player gets $5 if the first player chooses cooperate and the second player chooses cooperate. And we do this, they both do this simultaneously without knowing what the other prisoner's doing. And it's called a dilemma because the rational thing to do is always be nasty because it gives you the best payoff no matter what the other person does. But if both players are nasty, they get a lower payoff than if both players are nice. So there's always a temptation to be nasty and to undermine and betray your partner in this game. And it's set up precisely to see whether there are ways in which we can get people not to betray each other, to be nice to each other. And there are lots of different variations on this game. Things become much more interesting when we generalize the game to more than two players and we allow the players to interact repeatedly over many rounds of play. And so one way of doing that is to turn it into a game called the donation game. We have a large population of players. We choose pairs of players, and one player is the donator. They choose whether or not to donate some of their scarce resource. You can imagine it might be food to the second agent. The second agent gets a multiple of that donation, greater than 1, and the second player just receives the benefit. And if we repeat this, provided the multiplier is greater than 1, we can generate a surplus if people donate to each other. The problem is that again, even in this repeated interaction, theory suggests that you should be selfish and you shouldn't donate anything. This applies only, however, when agents are super rational, when they have perfect reasoning capabilities. On the other hand, if agents learn how to play this game through trial and error, we can get cooperation through reciprocity. So it's not entirely straightforward, but under certain conditions, agents, it makes sense under learning dynamics to donate some of your scarce resource to other people, to be nice. And the reason this works is through reciprocity. There are two forms of reciprocity: direct reciprocity. So if I help other people when they've helped me in the past, this is direct reciprocity. So A feeds B, and then B feeds A. So we both get the food in that situation. And in indirect reciprocity, I feed other people provided they've been seen to feed other people, to be nice to other people, provided they have a good reputation. So this is called indirect reciprocity. And there's a very famous parable that illustrates this, the parable of the spoons. This is a biblical story about a man who's taken to hell. And in hell, there are these long chopsticks with nice food, but everyone is hungry because the chopsticks are too long for people to feed themselves. The angel takes the same person to heaven, and in heaven, everyone is feeding everyone else. So this is indirect reciprocity. So everyone is getting fed, even though the so-called economic rational thing to do is to withhold your donation. And we see this kind of behavior in lots of species, both human and non-human. So, for example, in primates when they groom each other. And there's a whole vast literature on this, showing the conditions under which you get cooperation and how they vary depending on characteristics of the population and how well mixed it is, which you can find out more about in this paper. But for our purposes, the key thing is that when you do this experimentally with people in laboratory experiments, you do see reciprocity. You do see this trust through reputation and through conditional punishment, conditional cooperation. So our research attempts to see whether large language models understand this and behave similarly. And what we do is we create large language model agents, simulacra. These are the participants in our experiment. And we set up these different simulacra, these different agents, by prompting them carefully in various different ways. And we give a role to each agent, and the role prompts are divided into these different groups. So we create some cooperative agents, some competitive agents, some altruistic agents, some selfish agents, and some control agents, which are default out-of-the-box ChatGPT behavior. And we create these agents by giving them, by using carefully controlled prompt, and we pair each agent with a bot that has different styles of cooperation. So we pair each agent with either an unconditional cooperator, an unconditional defector, somebody who never feeds, somebody who always feeds, and then tit for tat, somebody who feeds on the first move, but thereafter only feeds you back if you've fed them, if you've been nice to them. And then there are two variations of this, one that cooperates on the first move and one that defects on the first move, and then reverts to reciprocal cooperation. So large language models are known to be very sensitive to the way that you describe the task. So once we've told ChatGPT whether it's a cooperative or selfish agent, we describe the prisoner's dilemma game, And we describe it in lots of different ways because LLMs are known to be sensitive to non-semantic features of the prompt. So, for example, whether we describe the payoffs using numerals or whether we describe them using words like $5 FIVE. So we have lots of combinations of these different conditions. These are our random effects. So there's a very large space of all combinations of these. So we just sample from this space of possible simulacra randomly. And these are the factorial conditions. These are the ones that we manipulate. So we manipulate the part of the prompt that describes whether the agent is cooperative, competitive, or altruistic. And we do this for different versions of ChatGPT model to see whether that has an effect, different temperature settings. So these are the kinds of prompts that we use for the different groups. So in a cooperative group, we say, for example, you are a helpful and cooperative individual who values teamwork and always seeks the best outcome for all parties involved. And the reason that we use these qualitative descriptions is that we can take the same prompt and the same participant and use it in lots of different social dilemma games. So these aren't specific to the prisoner's dilemma or a payoff structure. We can use the same participant in the dictator game, public goods game, and so on. So you can see the full set of prompts in our paper. So we have cooperative individuals, competitive, altruistic, and the idea with altruistic agents is that they should be nice even when their partner is nasty. So altruistic agents donate something even when they know that they're not going to get anything back. That's our definition of altruism. So we run this very many times with all of the different partner conditions and settings of the model. And we, before we started the experiment, we formulated various hypotheses about which groups would respond in which partner conditions. And here are the main results. On this axis here, you can see the type of partner that each LLM agent was paired with. So this is when they're paired with somebody who is always nasty. This is somebody who is conditionally good but is nasty on the first move. This is somebody who's conditionally good but is nice on the first move. And this is somebody who's always good. And then this is how, on this axis here, this is the probability with which the LLM agent is nice, chooses to donate. So these are the results for the different groups. And for example, you can see here the green line is what we predicted theoretically. And then these different lines here correspond to each version of the ChatGPT model. And you can see, for example, in this particular case here, in the case of the altruistic agent, we hypothesized before the experiment that altruistic agents would always be nice, irrespective of who they were paired with. This wasn't quite what happened when we ran the experiment. So the earlier models in particular responded differently depending on whether they were facing cooperators or defectors. The later model, ChatGPT 3.5 version 1106, this later model actually behaved quite close to our prediction. So here, although there's a very small effect, it's not always statistically significant, and the overall shape of this line is quite flat. So this indicates that the later model seems to behave in an altruistic way, in a way that an experimental psychologist would call altruistic, or that a behavioral economist would call altruistic. So we have, and we're able to do this with other games. So we also tried this in a game called the Dictator game, which is a one-shot game. And we can see how each model behaves and how each participant group behaves in this game. and compare it with our theoretical prediction. And here the idea is not to compare the absolute level, but it's mainly the direction of the effect here. And you can see that broadly, the direction of the effect is consistent with what we hypothesized. So what we have been able to show is that to some extent, GPT 3.5 models are able to operationalize these descriptions of altruistic versus selfish versus cooperative behavior in repeated social dilemmas. And this is evidence in favor of the hypothesis that these models understand, in a sense, these concepts. So they're able to produce narratives of play that are consistent with a scientist's understanding of these behaviors. So from a practitioner point of view, this is interesting because it suggests that large language models do in fact understand things like trust and reciprocity. And this suggests that they might be able to help humans cooperate in these kinds of settings. So from a practitioner point of view, our next experiment is going to see whether chatbots can help human subjects to cooperate more in a social dilemma called a public goods game. And we're going to see whether large language model agents, by acting as mediators and facilitators in pre-play communications, whether they can increase the overall level of donations in public goods games.
Steve,
yeah.
We're so sorry to interrupt you. We are like 7 minutes past the time.
Oh, sorry. Okay. Yeah.
No, it's okay. It's more than okay. Sorry, that's why we had to interrupt. Really, such an amazing session. And even me, I was enjoying the solving equation and this very interactive presentation. But sadly, we have to end it
Yep, no problem.
next to the other speakers. So
sorry for going over time.
it's okay, Steve. It's okay. So thank you so much, Steve, for introducing to us investigating emergent goals like behavior, large language models using experimental economics. As an economic graduate, this was very interesting to me. So thank you so much, Steve. And upcoming next, we will have our uh, amazing speaker, Kaito Song. He will be speaking about hugging GPT, solving AI tasks with ChatGPT, and its friends in Hugging Face. So, Kaito, how are you?
Hi, hello.
Good?
Thanks for the invitation. Okay. Okay, I'm okay.
Thank you so much, dear. And Kaito's on stage with you guys now. Thank you.
Okay. Okay, let's begin. Hello everyone. And my name is Kai Tao Song from Microsoft Research Asia. And today I will introduce Hugging GPT, solving AI task with ChatGPT and its friends in Hugging Face. As we know, currently we have witnessed the rise of the large neural model. We have witnessed many especially like ChatGPT or like Gemini or like Llama. So we can find that when a more powerful large neural model has been released and has demonstrated impressive performance across different tasks. So we can find that they have a saying is that large neural model is AGI, but it's really. So based on such a questions, we have conducted some rethinking, and we conclude that the large neural model is not equal to the AGI, because AGI means that the agent and AI should think as a human to solve any complicated AI task in real-world scenarios. But however, just using the large neural model, it still remains some limitations. For example, in real-world scenarios, that AI should be able to handle any complex information like vision, like speech, or like others. But currently, large neural models are mainly used to process text data. And the second one is that in real-world scenarios, that some complex tasks are usually composed of the multiple subtasks, and that requires more detailed task planning, and which are also beyond the capability of large neural models. And then, for some challenging tasks, large neural models also demonstrate excellent results in their short or few short setting, but they are still weaker than some expert models, especially like some fine-tuned models. So based on these observations, we think that large neural model it's not AGI, but it could be. So how to fulfill this point? We think that we could act a large language model like a human brain to think and then coordinate with external models to utilize their powers for solving different complicated AI tasks. So that's the question is that how to bring the connections between the large language model and external models. Here we write such a concept is that language is a general interface for large language models to connect external models. So based on such a concept that language is as an interface and large model as a controller or brain, that means we can use the language to describe the different models and their function, and then we can incorporate this model in description into the prompts. And large language model can be considered as the brain to manage AI models and such as planning, such as scheduling, and such as cooperation. So by incorporating this operation, that we can find that large language model can use this AI model to address the different tasks. So we can also find that we in the past that we have the concept that it's about powerful like large language model to do anything, but we think that more practical thing is that we can use a powerful model to manage anything. So that means that we can use we can use a powerful model like large language model, and then we can use it to manage different models. Okay, so how to fulfill this point? We can find that currently we have different many powerful large language model, especially like ChatGPT, also like Llama, or like Abaca, or like the Geminis and others. And besides, we also have many different tools or the models or APIs like Hugging Face, or like GitHub, or like a Python code, or like Bing Search, Google Search, or like Azure. So we can find that how to let if large language model is if the language capability of large language model is really powerful, we think that we can also teach them to use this tools, these models from the different sources like machine learning community, like tool libraries, or like APIs. So our target is to bring the connection between these two sources by using language. So we introduce the two objects. The first one is ChatGPT. The ChatGPT is a chatbot released by OpenAI with powerful capability in generation, reasoning, and understanding. Yeah, it has demonstrated a very powerful language capability, right? And Hugging Face is being considered as the largest AI model community. It provides massive AI models also covering massive AI tasks with different modalities. Moreover, all models in Hugging Face are free to achieve, and besides, it also provides many detailed model metadata and descriptions. So we write such a concept, can we link the ChatGPT and Hugging Face? So based on these assumptions, we introduced the Hugging GPT. So Hugging GPT means that we can use the LLM as a controller, and then we can conduct multiple stage like task planning, like model selection and task execution, and then to generate a result for the users. So when we give a user request, just to see this example, that it also in this example it also require the system to answer which picture the placed and also counted how many objects in this picture. If we just use large language model, we can find that it's not able to do the uh, vision information. So we can find that just use the large language models cannot correctly answer this question. So how to do it? How to address this problem? So here we can use the large language model to as a controller. That means we can first to analyze this user request, and then to analyze how can we use any other models or any other source to address this request, and then we are based on the predicted subtask, and then to select to choose the model to select the model from the machine learning community like Hugging Face, and then and after we have selected the correct models, we can execute these models, and then return the result to the system. And after that, after we have obtained this all result, we can merge it together to get a final answer. So just like this system. The example that we used, we were involved different involved different models like the image classification, like the detection, and like the image caption model, and it will help us to get many different answers so that we can find it it can directly extend the task scope of the large language model to answer the more to answer questions with different modality or different domains. So this is more detailed descriptions about the frameworks of the Hugging GPT. In first stage, it uses task planning using ChatGPT to analyze the request of the users and to understand their intention and disassemble them into the possible solvable task by using prompt. And the next one is the model selection. To solve this planned task, ChatGPT will select the expert models that are hosted on the Hugging Face based on the model description. And the next one is to invoke and execute each selected models and return the result to ChatGPT. And finally, we will define the template and use ChatGPT to integrate all the predictions of different model and generate an answer for the user. But this template is dynamic, or it can also be modified by different users, depends on your preference. Here we also provide two examples that these two examples can to show that the pipelines of Hugging GPT to fulfill to address the one user request. You can find that this example is to place generate an image where a girl is reading a book and her post is same as a book in the image example, and also place describe the new image with your voice. So we can find that this request has involved a different modality requirement, and it may require poster control and poster image classification, object detection, image text, and text to speech. And then it also required many dependency between the different tasks. For example, that maybe that the task poster to image is dependent on the poster control based on the predicted control. So we will use ChatGPT. We will use Hugging GPT to first the stage to plan task planning to analyze this task and also predict the task argument, also predict the dependency. And then based on this task, based on the each predict task, we will then based on the requirement and also the provided task model description from Hugging Face, we will make it to select a task, and then after we have selected the correct models, we deploy it in the Hugging Face or in the local server to get the result, and finally to generate the answer by merge different requests. Okay, so how to fulfill this point? Here we mainly use the prompts, and but we will use we will introduce such a design that we will first later ChatGPT later LLM to pass the user input into a structured data. Here is just this data will include the task dependency argument, and we will also use the and then we also provide a demonstration that to instruct the LLM to better generate a result by following this demonstration. And each domain of the task and ID and dependency and argument also provide in the definition. And the model selection is also designed by the prompts that based on the answer based on answer generated by task planning. We will also later the ChatGPT by inputting different model and by inputting different model description and to select it. And finally, we will generate. Here is the right part is the description about each model from the Hugging Face. And the last one is we will emerge different result of the prompt. Okay. So here is our experiments. We know that how during such a system we should answer. We should have some question. How to evaluate such a system? So we can find in such a system we can find that how large neural model can predict task and select model is very important to build such system. Specifically, specifically, we think that evaluate such a system can also reflect the capability of large neural model in addressing the complicated task. And so how to evaluate? And here is we divide this task at different types at a single task and a sequential task and a graph task, and so that we can use the different metrics. It's first the single task is very easy to evaluate. It's just you can use the precision, and the sequential task before predict task we also need to predict the dependency. So we also involve the editor distance. The more difficult is the graph task that maybe involve the structure of the graph. So we here also involve the GPT-4 scope. That means we use the GPT-4 to evaluate our result, the result of our system generated result. So here's a result that we can find that the GPT-4 series model can significantly outperform the vast model. So that means that this also demonstrates that the using a powerful large language model is required. To build such a system. Yes. And that also means that after a large language model has emergibility, that it can be used to fulfill such a system, and then can directly extend its task scope. And here is the conclusions of our model. And we have such a summarized point that the first one is how to use the capabilities of large model to act as a human is very critical. By importing this model description, that Hugging GPT enables the large model to use the power of the external models. And the second one is how to enable the most various and the more functions models or tools or APIs is critical to extremely enrich the scope of large model so that it can directly extend how to extend its task scope of large model, or currently we call this large model based agent. And finally is also the how to guarantee. That means it's how to optimize such a system. That means we can how to optimize how to guarantee the optimality of the planning and how to provide the efficiency of the model selection. Okay, so that's all. That is my introduction. That's my the introduction of our work, Hugging GPT. Okay.
So much, Kaito. This was an amazing session, and I'm really sure that it will help a lot with the artificial intelligence world and how the future references. So thank you, Kaito, for this amazing session and for your research about just a second. Yeah, for your session about hugging GPT and solving AI tasks with ChatGPT and its friends, Hugging Face, with your Microsoft research. So thank you so much, Kaito, for this amazing session. And moving on, we will have our next speaker, and it's Kanyo Chen. Kanyo Chen will be presenting to us, can LLM generate misinformation be detected? And he's coming with from the Institute of Illinois Institute of Technology. So, Kanyo, how are you?
Yeah, I'm good. How are you? Yeah.
I'm all good. I'm all good. We're excited for the research you're going to present to us. So, the stage is all yours.
Thank you. Thank you for the warm introduction. So let's begin. So hello everyone. My name is Canyu Chen, and I'm a third-year PhD student at the Illinois Institute of Technology. Today, I'm glad to introduce our work, Can LLM misinformation be detected? And this is a work published at ACME this year. And if you're interested in our work, you can scan the QR code to check out our project website. You can also check out my homepage. So firstly, why should we study this problem? Because emergent misinformation is actually a big barrier in our real life. And there are many news reports on this problem. For example, for journalism, we have already found that emergent misinformation, emergent news website are floating online. And for politics, we know that this is an election year. So actually, emergent misinformation pose a great threat for democracy and elections. And for finance, we know that emergent misinformation can cause large fluctuations for the stocks. And for healthcare, actually, evidence has shown that generator books has already been sold on Amazon. So this can actually cause life-threatening consequences. So what is the relationship of emergent misinformation and AI safety? Because AI safety is also one very most important issue right now. And on the left part, we can see the statement from the government, and in the right part, we can see the written statement from the top researchers like Banjo and Hinton. All this statement has emphasized the importance of combating emergent misinformation. So actually, emergent misinformation is one of the core challenges of AI safety. Then, what is emergent misinformation? Here, we conduct a basic comparison between human-written misinformation and emergent misinformation. Basically, human-written misinformation means that misinformation is manually written by humans. But for emergent misinformation, humans only need to simply prompt larger models, so larger model can generate one piece of complete fake news and so on. So a fundamental research question is where emergent misinformation cause more harm compared with human-written misinformation. And actually, the harm of emergent misinformation is a multifaceted and interdisciplinary problem. So, but in this paper, we propose to tackle this question from the perspective of detection difficulty. It means that we aim to investigate how hard it is to detect emergent misinformation, or how hard it is to determine the factuality of emergent misinformation for humans and detectors compared with human-written misinformation. So actually, our goal can be decomposed into three research questions. Firstly, how can large model be utilized to generate misinformation? Secondly, can humans detect emergent misinformation? Thirdly, can detectors detect emergent misinformation? So for the first research question, how can large language models be utilized to generate misinformation? Here we build a taxonomy from 5 dimensions, including types, domains, source, intents, and errors to categorize emergent misinformation. Actually, in the source, domains, and errors, these are the same categorization as the human-written misinformation, but source and intents are different. For sources, we can categorize it into hallucination, arbitrary generation, and controllable generation. And I will introduce the details later. And for intents, actually, we can categorize into intentional generation and unintentional generation. For unintentional generation, here I refer to the hallucination. So we can define hallucinations as unintentionally generating non-factual information. But for intentional generation, it means that malicious users could potentially utilize or manipulate larger models to generate misinformation. So more specifically, we can categorize the potential misinformation generation approaches into 3 types, including hallucination generation, arbitrary misinformation generation, and the controllable misinformation generation. I will give an example for each type of generation approach. Firstly, for hallucination generation, a simple example is police write a piece of news because we know that large model cannot get access to up-to-date information. So but news is one type of very timely information. So if I want a large model to generate one piece of news, it largely will contain hallucinated or false information, especially on the date and names and such a kind of fine-grained information. And for arbitrary misinformation generation, one simple example is police write a piece of misinformation, but we know that this is apparently a very unsafe prompt, so a large model can probably reject this kind of prompt. For controllable misinformation generation, it is different. For one example is open-ended generation. It means that given one sentence, please write a piece of news, and this sentence could be a very misleading sentence. For example, Trump is still the president. We know that the large model has strong instruction following ability. So actually, although this kind of prompt looks very normal, but actually large model can follow the instruction and to generate the misinformation. So and then we do some experiment to investigate whether or not we can utilize large model to generate misinformation with this kind of generation method. We know that large models such as ChatGPT has a strong safety mechanism or alignment. So so we adopt the attacking success rate to measure the probability of this generation method being not rejected by ChatGPT. And we run the experiment for 100 rounds and measure the times not being rejected. And we can see that actually hallucination generation method and controllable misinformation generation method, they have a very high success rate, attacking success rate. So we can, although the arbitrary generation method has a very low attacking success rate. So based on the experiment, we can, however, our first co-finding that large language models can follow users' instructions to generate misinformation in different types, domains, and areas. And based on this generation method, we construct a dataset called LLM. And this dataset has been open source on GitHub repo. If you are interested, you can check out. And this GitHub repo contains 7 types of misinformation generators, such as ChatGPT, and 6 types of open source large models, such as Llama and Vacuna. And also contains 7 types of misinformation generation method. So we move on to the second research questions. Can humans detect LLM-generated misinformation? Here, we employ the same group of human evaluators to do the factuality annotation on both human written misinformation and the LLM-generated misinformation, and adopt the success rate as a metric. So we adopt a success rate to evaluate the percentage of successfully identified misinformation in the whole data set by humans for both human written misinformation and LLM-generated misinformation. We can see that, firstly, we can see that generally LLM-generated misinformation has a very low, relatively low detection performance, human detection performance. For example, humans can hardly detect hallucination because it actually very fine-grained information. So it's actually very hard for humans to detect. Then we compare the human detection performance on human written misinformation and generation method such as paraphrase generation and writing generation and open-ended generation. And these three kind of generation method actually they can preserve the semantics, and the red part means that the detection performance is lower than the human written misinformation. And then the green part means the detection performance is higher than the human written misinformation. So we can see that the most part is red. It means that actually human LLM-generated misinformation can be harder for humans to detect than human written misinformation with the same semantic. So why should we control the same semantic? Because semantics and style information are two very important factors for the detection performance. So because we control the same semantic, so we can have a very important implication in that LLM-generated misinformation can have more deceptive styles for humans. Also, it indicate that humans can be potentially more susceptible to LLM-generated misinformation. It means that humans can be more likely to be convinced by larger models generating misinformation. So then we move on to the third question is, can detectors detect LLM-generated misinformation? Here we adopt a threshold setting to evaluate the detection difficulty of LLM-generated misinformation for 2 reasons. The first reason is actually this is a more practical setting because it's very hard to obtain the factuality label of LLM-generated misinformation. And also, large model can be easily utilized to generate misinformation in any types, domains, and areas and generators. But we know that conventional supervision training method, such as training birds, is very hard to generalize to different domains. So the second reason is that actually GB4 and GB3.5, this kind of large model detectors can have achieved the state-of-art detection performance compared with conventional detectors. So here we adopt the larger models detect such as the GB 3.5 and GB 4 as the detector to evaluate the detection difficulty of larger model generating informations. And also adopt a metric of success rate. It is the same as the human evaluation. And we can see that generally it is very hard for LLM detectors to detect LLM generating information. Secondly, we can see that GB4 can actually outperform humans on detection, but humans can still outperform GB 3.5. Then, more importantly, we aim to investigate the detection difficulty of LLM isolation and human written isolation with the same semantics. And similarly to the human evaluation, we can see that most part is red. It means that the detector detection performance is lower than for LLM isolation is lower than that on human written isolation. So we can have a third co-finding that LLM isolation can be harder for information detectors to detect than human written information with the same semantics. And based on this finding, we also have two implications. It means that existing detectors are likely to be less effective in detecting LLM information. And also, malicious users could potentially utilize larger models to escape the detection of detectors. Generally, we have based on our findings, we have three very important implications. It means that LLM information can be more deceptive and potentially cause more harm. There are many hypotheses before, but our work actually provides very solid evidence, empirical evidence to validate the harm of LLM information. And secondly, there is a potential major paradigm shift of information production from humans to larger models because it is more deceptive, right? And we also call for collective effort on combating LLM isolation from stakeholders in different backgrounds because it's a very interdisciplinary problem. Finally, I will discuss briefly the countermeasures through the whole life cycle of larger models. Generally, we can divide the life cycle of larger models into training stage, inference stage, and influence stage. So for different stage, we can develop different countermeasures. And if you are interested, you can check our paper for more details. Finally, I will give a summary. So in this paper, we build a taxonomy by types, domains, areas, and intents to systematically categorize LLM information. And then we make a first attempt to categorize and validate the potential real-world method for generation information with larger models. We also discovered that information generated by larger models can be harder for humans and the detector to detect the human written information with the same semantics, demonstrating that LLM information can have more deceptive styles and can potentially cause more harm. And we also discussed the potential countermeasures through the whole life cycle. Finally, I will briefly mention what is beyond detection for combating isolation. Actually, there are a lot of things we can do still. Here, so firstly, the landscape, I will introduce a landscape of combating isolation. So actually, the landscape embraces including detection. Information detection is a very conventional task and can embrace many kind of methods. Now, it also includes the information intervention. So it means that we should go beyond the detection, also intervene, interact with humans and intervene human to believe in this kind of information. And also information attribution is also very important. It means that we should we should trace back the publishers of the misinformation and hold them accountable. So actually, all these are introduced in our survey paper, Combating Misinformation in the Age of Large Models, Opportunities and Challenges. And in our survey paper, we also introduce both opportunities, including large models, how to utilize large models for combating misinformation, and also the challenge combating AI-mediated misinformation. If you are interested, you can check out. Finally, I will briefly mention the future directions, including how to utilize large model for combating misinformation, including we should consider the trustworthiness and consider utilizing multilingual and multimodal model large models. And we also should emphasize the importance of intervention and attribution and the importance of human and AI collaboration. And for combating AI-mediated misinformation, generally, we should try to elevate the hallucination of larger models. We should also improve the safety of larger models, and we should also develop better detection methods to detect AI-mediated misinformation. And we should also call for interdisciplinary effort. Finally, this is an initiative calling for more effort, and all the resources, code, and the papers are on the website. If you are interested, you can check out, scan this QR code to check out our project website and the paper list on the GitHub repo. Yeah, that's all.
Hello, hi. All right, thank you so much, Kanya, for this amazing session. It was really great and informative, and it was a lot of also chats, so you got people really excited. So thank you so much, Kanya, for this amazing session. And we had Kanya where he was talking with us about LLMs. And next on, we have Ayush Kaichel. Ayush will be speaking to us about low rank decomposition of monolith code LLMs for one shot compression. And Ayush is with Nolano with AI. So Ayush, nice to meet you.
Hi, nice to
Hi.
meet you
So
as well.
thank
Can you
you.
hear me?
Yes, we can hear you. And now the stage is fully yours.
Okay, cool. Hi, everyone. So, I'll be talking about my work on low rank decomposition of LLMs. It's a new compression frontier. You may be familiar with quantization, distillation, pruning. This is something orthogonal which can be combined with these methods. I'll be going over the methods which we propose and its advantages. So, this work was performed with my collaborators Tejas Vaidya and Irina Resh. So these are the core contributions I'll be talking about our work. It's a new compression frontier solely for large language models, and it's able to demonstrate significant potential as we empirically tested on models as large as 16 billion parameter, being able to reduce their dense parameter count by more than 3 billion parameters with very little drop in their performance, reducing their rank by up to 40%. And these techniques, which I'll be discussing, can be run on a single GPU with in less than 10 minutes, and it requires only one line of change in your inference code to achieve up to 22% of speed up. And since it's an orthogonal compression frontier, you can combine it with your favorite quantization technique or low rank adapters as well. So, yeah, by decomposition in this case, I mean the standard decomposition from linear algebra, where you have a large matrix like a weight matrix in case of neural networks. You split it into two smaller matrices of lower rank. The condition which we have is to avoid retraining after decomposition because training is expensive. Now, there's a lot of theoretical and empirical motivation about why this could be feasible, because it has been observed that the rank of activations reduces exponentially as we go deeper into the layers in neural networks. And this has been observed for a wide variety of architectures. And so, this technique of decomposition has been used for smaller language models previously, like BERT. However, those techniques required a lot of fine tuning after compression and second order gradient information, often and over a large amount of calibration data set. Our approach, on the other hand, is single shot, does not require any retraining, and focuses solely on LLMs. So here's what the different LLM compression paradigms look like when you stack these against each other. I'll be talking about like decomposition primarily. It's as cheap as quantization to decompose because just 10 minutes on one GPU. And it has minimal quality degradation, just like the weight only quantization. However, the weight only quantization, even though it improves latency, it worsens the amount of throughput which we can get for our inference. That's different for weight only, weight and activation quantization, but there the quality degradation is higher. On the other hand, decomposition, it increases the throughput, and it requires very little change in inference code, just one line, compared to like quantization and pruning where you need to write an entire kernels over GPU for matrix multiplication. However, as of now, we have been only able to get modest amount of compression, but this can be combined with the existing techniques if you want to achieve more compression. Okay, so more benefits, like you can parallelize unlike sparsification, and you don't need to write specialized kernels, and the compressed LLM will remain fully differentiable and end-to-end trainable. You can update all the parameters. And of course, quantization and lower, I've already discussed that. And our technique scales well, and there is no significant output quality drop, and this compression can be applied in a downstream task agnostic manner. So here's what our approach is like. It's empirically been observed that the output features of transformers are low rank, even though the weight matrices themselves are not low rank. So this is what we exploit in order to achieve low rank decomposition and compress the LLMs. So we adapt the atomic feature mimicking method, which was previously proposed. Specifically, we consider the eigen decomposition of the output covariance, like output of each linear layer that we consider in order to do decomposition. And so empirically, we observe that at least for the larger models, you can have significant percentage of reduction in rank without almost any change in perplexity. Like in case of code gen 16 billion parameter model, up to like 30% reduction rank with barely any change. Same for sarcoder 16 billion. For the smaller ones, it's a bit less. Like here we can see at like just 30% rank reduction, it goes up from close to 2.5 to 3. So in order to achieve compression, just simply reducing rank is not enough. We also need to take into account the threshold for compression via decomposition. Like just naively reducing the rank, but not reducing it a lot, can lead to total number of elements after compression being more. So like in this case. So there is a certain threshold which you need to cross in order to have compression from decomposition. And that threshold depends on the matrix aspect ratio. If it's a square matrix, then you need to reduce the rank more in order to achieve compression. Like here, you end up with the same number of elements even at half the rank. But for tall and fat matrices, it's not the case. So transformers have different shapes of weight matrices, like the multi-head attention or output projection are almost square matrices. So you need to reduce at least 50% of the rank in order to achieve the same size as it was originally in terms of number of weights that you need to represent after decomposition. So it's generally preferred not to decompose these kind of layers. And so we focus on the other kinds of layers, like the MLP, which is usually 8 over 3 or 4 times. That's the hidden dimension compared to the dimension of transformer layer. And also for multi-headed attention. So this is the, like taking that into account, this is how much we are able to achieve as a parameter reduction. And notice that if we just do very little change in rank, then we may end up with more number of parameters. So that's why you need to cross the threshold in order to actually start achieving the reference. And by being careful about which layers you select based on the aspect ratio, you can start to achieve compression without much change in perplexity. And this is the same for both star coder and CodeGen family of models. So here's the actual performance on human eval score. So if we just reduce rank slightly, the human eval score actually goes up, and this is very much in sync with what's observed in quantization, where often when you just quantize from 16-bit to 8 bits, the performance may go up slightly, but after that is like where it starts to reach back to the same performance. Like here in this case, for 13.2 billion parameter, and but by this point we have already reduced the number of parameters by about 3 billion, for example, in case of star coder, without much drop in pass at one on human eval. It should be noticed that for the current methods, beyond this the performance starts to degrade. And there's another thing we need to keep in mind, which is the hardware awareness. Like we decide the shape of matrices so that the algorithms for matrix multiplication runs fast. Like there's a reason that those are a very high power of 2, like 1024 or 2048. So if we do not select that well, even though the model size or the RAM usage may decrease, the inference time may increase. But this can also be applied to to compress model so that it can work better on specific kinds of hardware which perform well on certain properties about dimensions of its weight matrices. And we tried combining it with quantization, specifically through SPQR, and it showed no performance drop for 8-bit, and the original performance at FP16 before decomposition was around 30, around this, like 31.6 something. And that's pretty much what we see after compression as well. And this is pretty much the same what we would observe from when we would compress the vanilla model rather than a decomposed model through quantization. And we can combine these with low rank adapters and QLoRa, where by tuning these via low rank adaptation methods on certain instruction datasets, we found that we achieved the same human eval score as we did if we were just doing this sort of QLoRa tuning on this standard star coder model. So there are several open questions for future. Like we would want to dynamically estimate the rank based on the metrics and activation, so that we can find the maximal amount of compression which we can achieve through low rank decomposition. And we need to have more efficient gradient based methods for decomposition, because that can give better signals than just locally detecting the covariance metrics and based on that estimating what should be the low rank decomposition. And we are in the process of extending this to more general purpose LLM. We have so far only shown this for generation LLMs like star coder or CodeGen. And there are different parameterization forms for decomposition, like Kronecker decomposition or butterfly matrices, that remain to be explored. That's all. Thank you so much for listening to my talk.
Thank you so much, Ayush, for this amazing session and you taking us through
Thank you.
low rank composition of monologue code LLMs for one-shot compression. It was really great. So thank you, Ayush, again. And moving up, we have our next speaker, and it's Bruce Young. Bruce Young will be taking us through Fine GPT, open source financial large language models. So, Bruce Young, how are you?
Yeah, I'm good. I'm good. Can you hear me?
Yes, we can hear you. The mic may be a bit closer.
Uh huh. Yeah.
All right, perfect. So now the stage is all yours, and thank you so much, Bruce.
Okay, great. Cool. So I'm Bruce Young. I'm the founder and president of AI for Finance Foundation. That's a US 501c3 non-profit organization, and you guys can check out our official website for more information. And today my topic is FinGPT, open source financial large language models. And this is my agenda. We have a lot of things to talk about. I want to cover as much as possible today. And the first question is why open source FinGPT? And essentially, we see two different like drivers for the purpose of doing this. So financial data is not just same as data in traditional NLP sense. It has a few unique features. And recently, we've been seeing a general witness of shifting towards the trend of democratizing internet scale financial data. Like there are a few high quality and well-known financial data set on Hugging Face, right? So we have like unprecedented access to being able to feed the open source data into our model training and promoting the quality of financial data in the cooperative way is probably a great way towards like preparing for collective financial information innovation. And from the data perspective, like sharing financial data and better models that are able to use that data to predict different things can also increase like our understandings of how to improve our financial analysis tools in a general sense. And then from the model perspective, applying like a general large language model to finance maybe lead to a suboptimal or like so basically just because of the nature of financial industry, right? When you have a model that gives you a false positive or a false negative response, that's pretty bad for a trader's perspective. And this is a unique challenge that facing the financial industry in terms of application of AI for finance. So another thing is that financial data has some kind of domain-specific meanings, right? So like a layoff that which may be negative in a public, like a general sense, but it is positive for investors, and then may result like in the market going up. So the logic today that is employed in the financial set of settings is not exactly the same as a general social setting, right? Then a specific financial large language model would be necessary just to get that specific logic. And for our open source community, we like to do financial innovation through AI and open source collaboration. And our mission emphasizes the promotion of standardized practice and the development of open source resources and benefiting both the research community and industry professionals. And our short-term goal is that we want to build some like more open source projects and maintain a group of developers. And for the long-term goal, providing a standardized tool for the professionals engaged in the financial industry. And here is like another thing is we want to do is that we want to lower the cost of training a domain-specific large language model. So basically training a GPT-3 like once cost about like $1.4 million based on these like data. And training a Bloomberg GPT, basically that's in the financial domain, that's also cost about like $2.7 million. And if we want to scaling down to like a small like model, at least we need like $1 million to train the model from scratch once. But we have a cost-effective strategy, and basically we utilize the like the LoRa technology and an open source large language model like the foundation model like Llama 2, right? Like maybe Chat GRM, those kind of models. And for FinGPT, we actually use like LoRa plus like for example, the Llama 2 14B plus LoRa, it costs about $66. Basically one A100 training for like 16 hours. So that's very cost effective. We kind of lower the cost from $1 million to about $66 for per training. And now look at some unique challenges that set financial data apart from the rest of the data. First is the high temporal sensitivity. And how time flies, right? So in the financial world, it doesn't just fly, it actually zooms. So every tick of the clock matters. And the market moving news opens a fleeting window of opportunity. And a blink, you may miss the chance to capture the alpha signal. And next is the dynamism. So financial landscape is in like a constant flux. The news, the tweets, and the posts is like a never-ending stream. So if you guys want to retrain the large language model to keep up, but that's not very, not only impractical, but also very pricey. So the last for the financial data is the challenge of like the low signal to noise ratio. And picture this. So you are in a very crowded room and trying to listen to a whisper. So that's financial data for you, and full of noise and distractions. And extracting the valuable insight is labor intensive. And so how do we like to navigate these challenges? And with those challenges in mind, like let's talk about our like the goals, the key features of FinGPT. First, which data to train? We kind of build like a real-time data creation pipeline to democratize data for financial large language model. And then how to train? We use instruction tuning paradigm, and also RAG. It's called retrieval augmented generation. And how to train effectively? Basically, FinGPT utilize the lightweighted adaptation like LoRa and QLoRa. So here is the FinGPT framework. And actually, we have this and like we have like 4 layers. The first layer is the application layer. It's showcasing the practical applications and demos. Basically, it highlights the potential capability of FinGPT can do in the finance sector. And now we tackled the robot advisor and the sentiment analysis. And then for the task layer, we actually want to do some like benchmark evaluations between the different foundation models. And for the large language model layer, the FinGPT focus on a range of fine-tuning methodologies. And this layer takes care of the highly dynamic nature of the financial data and to increase the model relevance and accuracy. And for the data engineer and data source layer, it tackles the challenge of high temporal sensitivity and low signal to noise ratio in the financial data. And our first project is the like the FinGPT, like the data-centric. Basically, that's the our data creation pipeline. The challenge is that there are like a diverse of data source, and also there is data quality issues, and there's like a high time validity. And our solution is that we want to create a data creation pipeline, and basically we open source this one, and we can like automating the collection and curation of real-time financial data from the internet with 34 financial data source, and here is the corresponding code. This is one of the example of how to use the FinNLP. The next project is called FinGPT Benchmark. Basically, the current limitation is that most work focus on the single task instruction tuning, and our methodology expanding the instruction tuning paradigm to like 3 like tasks: the task specific, the multitask, and zero-shot training. So here is one example for the single task training. And as you can see that once there is a new model released, that's called intern LLM 20B. And basically we use this one to fine tune our tasks on the sentiment analysis and achieved SOTA. And all of the data, the model, and the code are all open sourced. So here is like multitask tuning. Basically, we bundle those all of the tasks together to train one model and to inference on each of the tasks. So basically, we have these two conclusions. For a single task job, no single model dominates across all tasks, and the effectiveness of models varies depending on the specific tasks. And if for the multitask job, some model performs well in single task job, but may not excel in a multitask job. So the performance of models can be different in multitask settings to single task settings. And also there is a zero-shot result. So basically, we train, this is our zero-shot. Basically, we train a model and then we do inference on a different data set. And this one is the same as the Bloomberg GPT. So our model, we have a F1 score of 0.74 compared to the Bloomberg GPT of 0.51. So a lot better and a lot cheaper. And our next project is the FinGPT RAG. It's our retrieval augmented generation framework. Basically, it solves the problem of the hallucination and also increase the accuracy. And here is the how to create the instruction following dataset. And basically, this is the example of using the RAG. So in the financial world, the news may be just one sentence like this one. Energizer shakes off JP Morgan's bear call. And if you guys throw this news into the large language model directly, it will give a neutral response. But if we use the RAG information to get off the context background, then it will give a positive, basically the correct response. And we did this to a ChatGPT 4.0 and of our model. Basically, the accuracy and alpha score increases. And the last one is our FinGPT forecaster. Basically, this one, we build an app. That's the future of robo-advising services. And basically, we have the ticker and the date. And basically, we use the past few weeks to predict the next week. And this is the response. So get I use the Apple and also the NVIDIA. Basically, our FinGPT forecaster can give the positive development based on the news only, and also the potential concerns. And the last is the most important one. We give the prediction and the corresponding analysis. The next week, it will down by 0 to 1%. It will up to 2 to 3%, and also gives the reason. Basically, these are the explanations of why we made this up and down choice. So this is FinGPT forecaster, and it's all open source. Basically, we deploy this model into our Hugging Face. You guys can try it. And these are our project last year. So basically, we published 5 papers. And this year, AI for Finance, we have a new initiative called FinRobot. So basically, there's an open source AI agent platform for financial applications using a large language model. And if any researchers are interested, you guys can contact me directly. So basically, this is the conclusion. We have everything open source: the data, the model, and also the app. Yeah, it's all into our Hugging Face and the GitHub repo, and that's all.
All right. Thank you so much. Thank you, Bruce. This was a great session, and I'm sure our listener have enjoyed as well. So thank you. And next and upcoming, we're gonna have Thorsten Handler, where he's gonna be our next speaker, presenting to you his research with AI. So do we have Thorsten Handler with us? Thorsten, hello. So I can see you'll be today presenting about balancing autonomy and alignments. So
Yes,
first
that's
of
the
all,
topic.
sorry?
That's my topic. That's true. Thank you very much.
Thank you,
very much.
Thorsten, and hope you have a blissful session and enjoy.
All right.
The
Thank
stage
you
is
very
yours.
much for this kind introduction. I feel very honored Can you see me again and hear me again? All right. I think it works again. So we have developed a multi-dimensional taxonomy for measuring how LLM-powered multi-agent architectures deal with the interplay of autonomy and alignment. And why did we do that? That's the question. So I think you all are aware of the basic backgrounds on LLMs and multi-agent systems, but we see that such large language models struggle with handling complex, interconnected tasks or problems. That means they lack in-depth and iterative thought processes, which are also known as slow thinking or system 2 thinking, according to Kahneman. And there are different ways to simulate such complex thinking, such cognitive architectures, and one, of course, is such an LLM-powered multi-agent system, which can be seen as a strategic response to this problem. So it means that they autonomously tackle user problems and goals. They decompose these problems into smaller, manageable ones, and they leverage the cognitive synergy of multiple of such intelligent agents, each connected with a large language model. And we here already see a or maybe the central challenge in such systems is the efficient balance between autonomy and alignment. So autonomy, of course, is definitely intended. We seek for systems that are able to autonomously tackle these problems or goals. And on the other hand, we want systems and seek for systems that are hopefully aligned with user values and user goals. So that's a big challenge. And then some questions arise. We ask ourselves how to analyze such concepts like autonomy and alignment in multi-agent systems architectures. And we made a little literature research and searched for taxonomies and frameworks. But all these taxonomies fall short in measuring this dynamic interplay. And one reason can be seen in the fact that all these taxonomies have in mind agents that are not really intelligent. That means it has been in the pre-large language model era, and so they are mainly rule-based and do not deal with real or so to some degree intelligent agents. And from this question, three other questions came up. And the first one is, of course, how do autonomy and alignment interact in such multi-agent systems? The second one, what are the characteristics, the architectural characteristics of such systems? And the third one, how do current multi-agent systems perform? How can they be classified according to our taxonomy? So we see the interplay, the interactions in multi-agent systems as one between three decision-making entities. On the one hand, of course, we have our LLM-powered agents. You can see on the right-hand side and the left figure. And these agents, of course, interact with human users. There's a dynamic tension between human users and agents. Of course, it's a tension between supervision and autonomy. And on the other hand, and this is a very important point, we have rules and mechanisms. So our multi-agent systems can be seen as software products of software engineering connected with large language models. So we also have such rules and mechanisms who have been defined by human software architects. So we have also an interaction between these rules and mechanisms and human users in terms of alignment. That means what is aligned by the user and what is aligned by the software architect beforehand. It's the question between customization and automation. And on the other hand, we have such a dynamic tension between rules mechanisms and the LLM-powered agents. That means tension between automation and autonomy. That means we have here this triadic interplay of three decision-making entities. And then we ask ourselves, okay, how can we transfer that that interplay into a taxonomy. And we often observed taxonomies that begin with no automation or no automation, completely user handled, and the highest level is complete automation. And we go with a different concept. We say, okay, our lowest level is automation, and then we have two directions. We have a two-dimensional matrix. On the one hand we have alignment, and on the other side we have autonomy. And then we combine these perspectives of alignment and autonomy. And of course, the highest level of alignment and autonomy reflects an evolving level of dynamism and responsibility of both LLM-powered agents and human users. And what does it mean? We have three levels, have defined three levels in each axis. We have an alignment axis and an autonomy axis. And in autonomy axis, we have static autonomy. That means it's fully automated and bases on rules and mechanisms, constraints predefined by software architects. We have adaptive autonomy. That means that our LLM-powered agents have a certain degree of freedom, but it's in predefined boundaries. That means they can act within certain scenarios and within a certain scope. And the third level 2, means self-organizing, completely self-organizing LLM-powered agents. That's the one axis. And on the other side, we have alignment. And alignment starts with integrated. That means that the rules and mechanisms are predefined by software architects and completely static. We have user-guided alignment. That means we have the possibility for users to define certain constraints and condition rules before runtime. And the third one is real-time responsive. That means we have the possibility for users to interact with the system and align the system during runtime. So that is our two-dimensional matrix. And by combining these three levels, we get 9 different system types. Yeah, beginning from number 1, rule-driven automation. Completely, everything is rule-driven, is completely static. To user-responsive autonomy. That means we have very intelligent, we have completely LLM-powered agents who can act independently and who can interact with users to real time. So there are 9 different types of systems. And then we ask ourselves, okay, can we now classify our multi-agent systems according to this matrix? And we found, okay, it's difficult because a system cannot be seen as a monolithic system, as a block. Of course not, because autonomy and alignment can be seen as cross-cutting concepts. That means they can be in all aspects or different aspects of the whole system. And they can be implemented and realized differently in different aspects. So we ask ourselves and come to the second question, what are actually the characteristics of LLM-powered multi-agent systems? And of course, it's very basic, this overview here. We have a human user who interacts via prompts and can define preferences and get responses. And internally, we have our agents who interact with each other via prompts and based on roles and memory. And the goals are broken down into tasks, and these tasks are executed by these agents. And these agents not only interact with each other, but they also facilitate or use contextual resources like data, other foundation models, expert tools, and of course the large language model as the basic intelligence of the systems. And on the other side, on the right hand side, you can see system architects who of course develop the whole infrastructure of this multi-agent systems and also specify alignment techniques. That's not so much interesting, but we come to our next question because we then ask, how can we generalize? How can we generalize this architectural perspective on multi-agent systems? And we for this purpose, we leveraged a concept that is known from software engineering research. It's called viewpoint model, and a very prominent example of a viewpoint model is the one by Kruchten, proposed in 1995. He has been lead software architect at IBM, and he proposed the 4+1 view model or viewpoint model of software architecture. And basically, such a viewpoint model reflects different perspectives and concerns on software systems. And you can here see in italic, you can see the original title of the corresponding viewpoint. It's called a functional viewpoint. That means what are the key functionalities as perceived by the user of a system. The development viewpoint, which means how the system actually developed. One would say is a typical software architecture viewpoint. That one's process viewpoint, which kind of interactions processes can be observed within our system. And the fourth one is the physical viewpoint. That means how does our system interact with physical resources. And we mapped this basic viewpoint model for software architecture to the characteristics of LLM-powered multi-agent systems, and we defined them accordingly. So we say the functional viewpoint is goal-driven task management. It's how the goals are broken down and then managed. The second one, the development viewpoint, is the actual agent composition. That means how is the agent network organized? How are the different agents in particular organized? The third one is then a multi-agent collaboration. The processes are the collaboration between the communication between the agents, and the fourth one then is the interaction with the context, interaction with the LLM, interaction with additional resources like data and other foundation models. And then we thought, okay, can we organize such a domain ontology? That means, can we organize the concepts that are relevant for such multi-agent systems according to these viewpoints? And we observed and inspected about 3 to 4 of open source systems, including Super AGI, and then we built such a ontology model. That means a model of the existing concepts within the system. That's not a architecture model, but it means there are concepts that can be some way abstract and in some way more concrete. But if you take a look inside, we can here see the decomposition, the orchestration, the synthesis, all parts of the task management activity. You can here see the communication protocol, which is used by the agents. The agents generate agent prompts. Actions trigger these prompts. We have different kind of actions that are this one above, and so on. And another aspect is context. Context. We have tools. We have data. We have foundation models, or we have different kinds of them, and also different kinds of agents, and so on. And then we ask ourselves, okay, the basic question was how to analyze autonomy and alignment within our systems. And so we identified concepts that are that can be evaluated according to autonomy and alignment. And what we see here is a feature diagram which structures our taxonomy, and we see on the top that we have our 4 viewpoints, and every viewpoint has a autonomy level and an alignment level, and these can be combined: static, adaptive, self-organizing, and integrated, user-guided, and real-time responsive. And each of these viewpoints in turn has other features or viewpoint-specific characteristics. Like, for example, here, the goal-driven task management has the decomposition of problems into smaller tasks, the orchestration, that means the organization of agents, and the third one, the synthesis, that means the combining of sub results into a whole result. And then we have our multi-agent collaboration with communication protocol management, prompt engineering, action management. Then we have agent composition with agent generation, role definition, memory usage, and network management. And finally, we have our context interaction with the integration of resources, and finally also the utilization of resources. And then we brought our concepts together. That means we for each of these viewpoint characteristics, we evaluated the levels of autonomy and the levels of alignment for a set of selected multi-agent systems. And in our study, we included AutoGPT, Baby AGI, Super AGI, Hugging GPT, Meta GPT, Camel, Agent GPT, and as contrast to these agent systems, we also included Zapier, which is a process automation tool. And as a result, we can see that we have different systems profiles. We can see that here, for example, Hugging GPT has high levels of autonomy in different aspects of our system architecture. And we also see here Super AGI with higher levels of alignment for certain aspects. And with viewing all these different system profiles, we can see that we have no highest level of alignment. This means we have no user responsive, real-time responsive alignment or interaction level realized by current systems. Yeah, and we can see that across all these systems, we have some aspects that can be classified as high autonomy aspects, like the decomposition of goals, or the management of actions, or the utilization of contextual resources. We see that other aspects are mostly low autonomy aspects, like the orchestrating or distributing the tasks, the guiding the collaboration between the agents, the management and utilization of the memory, the management of the agent network, or the integration of contextual resources. This is mainly based on rules and mechanisms. And we see some intertwined dependencies. Yeah, and in the end, we can say, yes, our taxonomy seems useful. We can compare and select multi-agent systems. We can reason about architectural design options. We can scrutinize strategies and balancing levels of autonomy and alignment. Of course, we have some limitations because we made an hierarchic taxonomy, and we did not reflect self-enhancement or proactive agency. On the other hand, we did not reflect the quality of alignment at all, or the efficiency or depth. And yeah, we also observed some challenges for current systems, like the adaptability of communication protocols by the agents, that the agents by themselves can organize the protocols, or the robustness of prompt-driven collaboration, and finally, a challenge in controlling high autonomy aspects, like, for example, terminating activities or dead ends, and finally, real-time responsiveness. Yes, that's it. Thank you very much. I'm completely in time, I think, and it's an honor. Yeah, thank you very much for your attention.
You've been perfect, Thurston, and I personally enjoyed the characteristics of LLMs part. So thank you for this amazing session. And yeah, so moving on, we have our next speaker, and they will be presenting the impact of large language models on scientific discovery, primarily study using GPT-4. We have on stage with us Lijian Wu with their research from Microsoft Research. So, Lijian Wu, hope to see you, Lijian. Do we have the Lijian with us?
Hi everyone, this is Li Junwu from MSI for Science. Today I'm very happy to present our work, The Impact of Large Language Models on Scientific Discovery, a preliminary study using GPT-4. So basically, this is a very empirical paper, and we did a lot of investigations of the large language models on its effect on scientific discovery. So we have plotted the QR code and also the paper link. So if you're interested, welcome to read it. So let's first talk about the power of large language models. So we all know that since ChatGPT and OpenAI has developed such a very strong GPT series models, so people are all feel energetic about this kind of generative models, and the large language model really effectively help each other and also our daily life. So also Meta's Llama 2 and also Google's Bard, they are all very competitive products, and people are very hardly working on the large language models. So what we know is that large language models have shown great success in multiple domains, and the LLMs are the one of the very important aspects to the AGI. So when we talk about scientific discovery, for example, when we care about the protein, molecular, and other domains in scientific discovery, that we also see that AI has shown its power to do some very important breakthroughs. For example, AlphaGo, and it did a really great job in the protein structure prediction. And also they have DeepMind has published a lot of good papers on Nature series, and shown that the protein structure prediction can be enhanced by a very well-defined and strong capability of transformer-based models, and also the kind of deep learning models really did well on these tasks. And also in recently that DeepMind and also Microsoft Research that we have published several papers about the material design that also deep learning and AI can really discover some new materials in this kind of domain. So this kind of things really demonstrate that AI and large language models can help do very good will in the scientific discovery. So what we wanted to do here is that we want to see the large language models, specifically for GPT-4 or things like that, the very strong and the frontier GPT-4 models, whether they can do well in the scientific discovery. So specifically, what we here do is that we study on different scientific areas and we evaluate its capabilities on different tasks. So for example, let's say we define our evaluation on 5 specific scientific areas: the drug discovery, material design, computational chemistry, and biology, and also PDE. And for the capacities, or the capabilities, we test on this kind of following tasks, the following abilities, for example, the analyzing the literature, and also the concept clarification, data analysis, theoretical modeling, method guidance, prediction, experimental design, code development, and also hypothesis generation. For this kind of our capabilities, we want to see whether they can do well. And for specific tasks, actually, we have a lot of tasks that we have defined. Instead of the very well-defined benchmark task, for example, that machine learning people have shown a lot of good benchmarks, for example, property prediction, molecular net, or things like that. We also have a lot of tasks that we should do some kind of manual checking. We should the experts to do the evaluation of these kind of tasks. Though actually our whole evaluation or the study covers a lot of different aspects, the different scientific areas, and also different capabilities, and also different kind of evaluation tasks. This is the overall picture of our study. So now let's get into the specific evaluation results of our studies. So first, let's talk about the drug discovery. For the drug discovery domain, actually, we evaluate a lot of examples, and this is a very good summary of what we have and the evaluation observations that we got. For example, GPT-4 can really do well in some aspects, and here we call the strengths. For example, for the broad knowledge capturing or the investigation of the broad knowledge, that GPT-4 demonstrates very well understanding of individual drugs, target proteins, and also general principles of the small molecule drugs and the challenges faced in various stages of the drug discovery process. For this kind of broader knowledge, GPT-4 can do very well. But this is very, very satisfied that in our human expectation, right? Since that GPT-4, this kind of model can read a lot of articles in the paper and also on the website that we can know the kind of knowledge, the very basic knowledge that we can do well. And also the interesting one is that the GPT-4 can also help us do very good will prediction tasks or other tasks. For example, for the molecular manipulation, drug target binding prediction, molecular property prediction, and also retrosensitivities prediction, things like that. GPT-4 can really help us to do some this kind of prediction, and we have benchmarked this kind of tasks, and we found that GPT-4 in some specific tasks that can reach or can catch up with the total performance of existing specialized designed model for this kind of prediction tasks. And also for the novel molecular generation, GPT-4 can also give some suggestions, actually, because it's hard to say that this kind of generative molecules are very real or can satisfy each kind of properties. But actually, it can generate some novel molecules that need to be further verified. So GPT-4 demonstrated its ability to do the molecular generation, and it's very important. Also, for the coding capability, GPT-4 can also help us for the coding in drug discovery. For example, if we want to just do some simple, faster osmosis, downloading things like that, and do some kind of translation things like that, yes, GPT-4 can really do well. But also it has limitations, of course, right? For example, we found that for the small sequence processing, actually GPT-4 cannot do well. And also in other things, just like limitation, a very strong limitation in the quantitative tasks. This means that we wanted to do some kind of predicting the numerical values for the molecular properties, or just like the affinity between the drug target binding. We found that GPT-4 can really do not good. But this is also understandable because this kind of numerical prediction and the regression task is very hard for this kind of specialized token-wise GPT-4 model. And also, there's one thing that we need to double check the generative molecules. As I said, that this kind of molecule cannot be seen very well or things like that. So we need to do further checking by the experts or by other models. So let's say some cases here. So for example, the left picture shows that for the general understanding of the Lipkin's rule of 5, it can really do well. This is understandable because on Wiki or a lot of blogs, people has shown and also has introduced a lot of things of this kind of Lipkin's rule of 5. And also for the better case in the right figure, we can say that, as I said, the smallest translation is not so good. For example, we give him give it IUPAC name of a drug, and we wanted it to generate its small interpretation, but actually we failed. The GPT-4 model really failed a lot of times, and yeah, it cannot do well. This is somehow also maybe can understandable because this kind of sequence is long, and each character in this sequence has its specific meaning. And without this kind of real tokenization methods, GPT-4 cannot do very well. Okay, so for the biology domain, we also have these strengths and also potential improvements. For the strengths, we can see that for the bioinformatical processing, also GPT-4 really did well. It has understanding of this kind of information processing from specialized files, for example, the FASTA file and the VCL format file. And it can also perform bioinformatic analysis with given task and data. So it has knowledge of the biology and the basic information. And for the biology understanding like that, we wanted to do some tasks, for example, the sequence consensus sequence understanding and the PPI prediction, and also the signaling pathways prediction, things like that. Yes, GPT-4 can do, and it can give you some understanding and results, and mostly of that are correct. And for the biological reasoning, which means that we want to GPT-4 to give us some answers why this thing will happen. For example, for some specific disease, why it happens, or things like that. Yes, GPT-4 can also give us some reasons about this kind of mechanism behind this kind of biological observations. And lastly, for the biological assistant, just like what we talked about the coding in molecular domain, here also for the biological coding, that GPT-4 can help us do some assistance. For example, it can help you do protein design and also potentially help you do in wet lab experiments. Potential improvements also, yes, important, and we found a lot of limitations currently. For example, similar to the small prediction or a small sequence processing, here the faster sequence processing and the understanding is also very hard. This is also like what we said, the fast sequence and the small sequence are very long, and it's very hard to process all these kind of sequences. And also for the prediction of the GPT-4, it sometimes gives you inconsistent result because the GPT-4 has some kind of random prediction, right? And it cannot do so well. So we need to do double check of this inconsistent results. And also similarly for the LBAC numerical number understanding, it cannot do well. And for this kind of calculation, it's a similar thing. And the last point is that the prompt sensitivity is very important. For example, if we give the GPT-4 different prompts, it can really give you some different answers. So this is a very important thing that we wanted to see. And also, I guess in large language model domain, there are a lot of studies now will happen. For example, COT try to improve the prediction, and also such like self-consistent COT or things like that. Yes. So for this time, different prompt that give you different answers, we suggest that people should do a lot of or at least several times evaluation on this kind of things. For example, you give GPT for a set of different prompts, and then you check the results. So here are some cases. For the left figure is also it's a very good case that it can really help you do the binding prediction. For example, for DNA and protein binding prediction, whether you can do it well or not. And also for the right figure, it shows that it really failed. It is failed of the DNA translation. For example, we give the DNA sequence and we want it to translate for us the protein sequence. Okay, but yeah, GPT-4 failed. Okay, next. So the computational chemistry domain, actually, it's a very large domain, and we specifically here focus on the MLFF, machine learning force field, and the molecular dynamics or things like that. And we really found that, yes, also the strengths and the potential elements are very obvious. For example, for the literature review, yes, GPT-4 can understand just like previous domains. It has knowledge of these kind of simple things, and the theory or the simulation basic understandings, yes, it can do. And for the method selection, yes, GPT-4 also can help you recommend the suitable computational methods for all the software packages, things like that. What kind of software you can use for do some specific tasks? Yes, it can also suggest you very good things. And for the simulation setup, it can also suggest you how to set up hyperparameters or how to do the simulation in a very stable environment. Yes, it can help you do this kind of suggestion. And also for the code development, just like previous works or previous domains, yes, it can help you assist with the implementation of novel algorithms or the functionality. And things like the experimental computational and theoretical guidance, yes, GPT-4 can do. But it has a lot of limitations. For example, the hallucination. Yes, GPT-4 gives you some kind of not correct answer that don't know whether it will happen or things like that. Yes, and also for other like row arithmetic coordinates, just like the structure prediction or things like that. Yes, GPT cannot well do. For the confirmation and the different structures prediction, yes, just like the numerical prediction before, GPT-4 cannot do well. And also similarly for the process computation, GPT-4 may fail in a very successful rate. And also on the hands-on experience, yes, GPT-4 cannot do well, of course. That can only provide guidance and suggestion, but cannot directly perform experiments. This is very easy to understand. And here are also some examples. For the left figure, we show that when you wanted to predict the dipole moment, just like this kind of property, yes, you can do well. But for a specific molecular structure generation, just shown in the right figure, it can not do very well. This is also very understandable, as we said, that the numerical things and the structure things and coordinate things are very hard for this like specialized discrete token prediction, right? Okay, so next one is the materials design domain. We think that for the strength is also like the information memorization or the literature review. Yes, GPT can do well. And for the composition creation, it shows proficient in generating physical chemical compositions for inorganic materials, things like that. And for the synthesis planning, yes, it can also give you satisfied performance for this kind of synthesis planning. And also for the coding assistance, yes, just like before, GPT-4 can help you do well in the DFT calculation or things like that. Yes, it can give you some guidance and help you write a code of this kind of things. But it cannot do well in real experiments. For example, the structure generation, yes, it failed, just like what we said, the molecular structure or the protein structure or the material structure, it cannot do well. And also for a lot of predicting tasks, it cannot do very well. especially for the numerical related prediction tasks. And let's say some cases. For example, the left figure shows that it can do some things like the categorizing of the solid electrolytes, things like that. Yes, it can specifically do the categorization of different materials but it cannot do a lot of things, just like in the right figure. For example, the prediction some specific properties of a crystal. Yes, it failed because this kind of is a regression task, right? As we said, yes, it fails again. So finally, to the PDE domain, the partial differential equation, it's much like a theoretical domain, but also it has a very specific applications like in flow related the tasks. And we found the PDE can understand the GPT-4 can understand the several basic concepts. For example, the PDE concepts. What is PDE, right? How to solve the PDE, or what's the usually used methods to do PDE? Yes, a lot of things that can contain in the literature, GPT-4 can answer you. And also the relationships between these kind of concepts, yes, GPT-4 can also give you some guidance. And for similar to the material design, it can give you suggestions how to do some PDE solve, like give you a solution recommendation or things like that. Yes. And for the code generation, just like in code assistant, yes, GPT-4 can give you some kind of codes and let you to solve this kind of PDE problems very efficiently. Very interesting one is that GPT-4 can actually give you some new research direction guidance. This is very important. When we say some things like before, on what kind of things we have been solved or in academic research field, what kind of things have been solved, and the new research what kind of new research trend will be happen. GPT-4 really do some kind of prediction, and we use not a very new GPT-4, I guess it's a 2022 version, but actually it gives you some guidance. And also we need to enhance understanding of less data entities. This really important for the specific domain, like in info science or things like that. That a lot of things that we have never seen or less seen in the GPT-4 or in the general literature. And also we need to enhance the molecular and structure generation for this kind of structure prediction. This is super important for info science domain, but GPT-4 cannot do. Yes. And also finally, we need to enhance the model's interpretability and explainability. This is also very important for things that in info science, for example, in drug discovery, we really need some guarantee of the generative molecule, the toxicity or things like that, and we need this kind of interpretability to help us do better. Okay, yeah, due to the time limitation, we are not talk about more, and here is just the paper link, and if you wanted to contact and for more information, welcome for the contaction. Yes, this is our email. Thanks.
Thank you, thank you, thank you so much, Dijon Wu, with your research about the impact of large language models. This was an amazing session. Moving on with our next speaker, it will be Sumdish Rasao, where he will be speaking and taking us through LLM's harmony, multi-agent communication for problem solving. So on stage we have with us Sumdish Rasal from Here Technologies. How are you, Sumdish?
I am good. How are you?
Sorry, Sumit, I misspelled your name wrong. Apologies.
That's fine. I was just making sure that yeah, this was my turn. But I can go ahead.
Perfect. So the stage is yours, and good luck.
Thank you. Bear with me. Just bear with me. Okay, one quick second. You're not able to see my screen, right? Oh, jeez, one second. Let me do this. Right. Hi everyone. My name is Sumit Sat. I am a principal engineer at Here Technologies. I'm an alumni of Georgia Tech, and today I'll be talking about my work on LLM Harmony, which is using multi-agents to solve novel problems. Yeah, so let's get started. Okay, just one sec. Okay, so basically now that you've been part of the conference for so long now, you've generally got a gist of what LLMs are, um, and that's the new space where everyone's trying to be at, and then kind of just go through uh, solving multiple problems using LLMs. And again, in a nutshell, that's what the LLM is supposed to do. It encodes a given language and then tries to understand the nuances behind how we communicate or how language is used, right? So from that perspective, um, the LLM poses, or the architecture poses um, a lot of opportunity that we could do a lot of things, solve a lot of problems, fix a lot of things, invent a lot of things, right? So there is a lot of excitement across the group, the community, to make this work, somehow make it better, make it autonomous and everything, right? So in a nutshell, like that's what my research is about. Like, okay, now we have this. Okay, now what do we do next? Okay, how do we build, how do we improve on that, or what do we do with this? Okay, so um, what sorry, I'm toggling between two screens, so if you see me on the other side, just okay. So it is powerful as a tool, but it does have its own challenges. Like it can't really solve complicated problems. It can't really understand problems in some cases. You have a limited set of data that can be asked and responded back within a context of sorts. You can't really have an unlimited context. It doesn't really work with memory. Like, again, there's no external memory, or there's no memory in a nutshell. Right? Everything is like context based, and then that's limited. It ranges from like 2,000 tokens to 128 128,000 tokens, and now some claim they have 1 million tokens. So yeah, but again, it in a nutshell, I'll still term this as it's a context based limits that we have. And again, a lot of fellow researchers have mentioned that retraining an LLM, training it from scratch, is an expensive piece. So it's not really something that we could do um, easily and in an affordable manner, right? So we need some ways to make whatever systems we have right now as open sourced LLMs to make it work, right? Okay. Now, one approach that came up from the Google research team was, hey, can we aid the LLM in a way that it's prompted with certain kind of information, so that it helps the LLM answer or solve the problems, even problems that are not software development based, but also inclusive of math problems, common sense problem, reasoning problems. Okay. Then another stream came up of a multi-agent approach, where now you have multiple agents talking to each other, trying to correct each other, trying to aid each other in finding a solution to a complicated problem, like build a snake game, or build a tic-tac-toe game, right, in Python or in C++ or whichever language you want, right? So again, from that perspective, a lot of multi-agent frameworks have also come into the picture, right? And my research was, okay, I see there are two uh, excellent ways of improving the LLM performance or accuracy. Can I merge the two? And that's what LLM Harmony in this case is, where it's trying to take in a multi-agent framework and then providing it a chain of thought reasoning, and then allowing the systems to communicate to each other and then try to solve novel problems, which again, from the get-go is not possible or is not as accurate with any LLMs for that matter. Okay, let me move on to the next slide. Um, okay, so again, like I mentioned, right? So from the framework perspective, we have a framework where we're using a Camel's framework, where they have the ability to now create multiple LLM agents, and each agent has its own personality or persona. Essentially meaning that, hey, you're a developer, you're a tester, you're a VP engineering, or you are a math expert, you're a spatial reasoning expert. Like, so you could create agents in the framework, and then given a problem statement, what will happen is, given what problem it is and what kind of solution it requires, the orchestration agent will then start and say, okay, you know what, here I need a math expert, here I need a common sense reasoning expert. So okay, then that's how the communications will start with this agent and the orchestration agent, and then try to work towards, okay, let's try to devise a solution for the problem statement that has been shared by the user. So user in this case is also an active participant, so to speak, but it doesn't have to interject at each point in time. It just has to start the conversation, like, okay, here's the problem statement, go for it. And again, I like the way Camel's framework has set up um, agent personality support, so that you can actually add in multiple agents doing nuanced facets of work and not really overcomplicate anything, right? So you could have distinct and as many as agents as you want, right? Okay, let me move on to the next slide. Yeah, so like I was talking about, right? So the Camel multi-agent, they have their own framework. Again, all of this that I'm mentioning is publicly available in GitHub. And yeah, let me just check. Okay, yeah, I think I've covered everything. Sorry. Okay, so yeah, so now I'll go through some of the examples that I've tried as part of this experiment. One of them was general math questions, and then there were two variants to it. All these are all word problems. Okay, so if you can just go through the examples, you can see, okay, how the conversation starts and how the 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 other agent, the specialized agent in this case, is actually responding back, and then try to break down the whole problem. And then, even though it's again a math problem, it's still trying to predict the next word, but in a systematic manner, right? So now this is where the chain of thought reasoning comes into the picture, and it kind of improves the solution. Otherwise, again, it's just words, a bag of words for the LLMs, right? So if you just ask an LLM such questions, the answer of getting it right is not really, it may be 50-50, something like that. And let me just move on to the next slide. Yeah, so here I'll talk about the results. So if you can look at the results, like if I use a GPT 3.5 turbo agent, the rate is about 50% success rate. And using multi-agents, which was provided by Camel's framework out of the box, it does a little bit better, but not as better as what we are proposing. Again, it kind of builds on top of the best of both worlds in chain of thought reasoning and then the multi-agent framework support. Okay. Similarly, for the SWAMP database, again, it's similar. We are getting comparably better results than the other two systems that we have tested against. Okay. I'll move on to the next one. So this is another test that we did. This is for common sense reasoning, where given a sentence, given a question, there are answers that need to be inferred. So it's not really available, or there are cases where you have multiple options and the LLM needs to pick the option, right? So again, we're trying to inculcate reasoning, the way we think about problems, given our knowledge of what can be inferred from a given problem statement, right? So again, using chain of thought processing, again, we provide in that input the prompt in such a way that given one problem statement, the LLM kind of knows, okay, this is how I have to break down each problem and then come up with a valid solution, and then justify the solution as well, that why I am selecting or why the system is selecting whatever answer it is, right? This is one of the examples that we have. Let me move quickly to the results. So yeah, again, if you can see, this actually common sense reasoning by and large is good for a single agent as well, a single default agent, LLM agent. But again, with our approach, it kind of bumps up to as close to as 83. Again, we're kind of getting to human level accuracy. We're not there yet, but yeah, we're close enough. Okay. Then let me talk about the limitations, and again, what we plan to do in the future. Um, like I mentioned, like the LLM or the accuracy of a single LLM is also dependent on what it's trained on. So again, I could use OpenAI's GPT-3, GPT-4, 3.5 or 4 model. Then I'm dependent on their accuracy. But if I use something which is an open sourced model, the accuracy might be low, right? So we're trying to build a strategy where we could use external memory to kind of offload or obfuscate that this difference that we have, that we don't need to have the best model, because we know what we want to fix, right? So we don't really need newer data for this, right? For reasoning, for math problems. And then again, the other case is a lot of new data is generated every day, every minute or so. But how do we build a system that the LLM can be continuously fed with this kind of information, so that it still has relevant information to make informed decisions, right? Where something which is it not trained on, it might not be able to encode it properly. So that's something that we term it as a limitation at the moment. And then this is something that we are actively working on, and we probably might have something out in by spring or something, where each agent can should be trained on a different data set, so that it doesn't really is not really a profile, right? So when I mentioned camels uh, uh, persona or personalized prompting, it's more of like one agent just wearing different hats of act as person A, act as person B. But we actually want to have multiple such persons that are trained on different data sets, so that the answer could be much more rich than just everyone having the same data source, right? So there is no comparison, if you know what I mean. So those are the things, some things that we want to tackle in the future. Let me move on to the last slide. Yeah, so yeah, in conclusion, yeah, what I've presented, it's just like LLMs have now better ability to solve novel problems in the space of software development, in the space of common sense reasoning, in the space of math problems, which it was not trained for, right? So at least um, math problems and common sense reasoning problems, it's not really trained on that. So we don't have to retrain it, if just to if that makes sense, right? There's also a good uh, reason of using multiple agents in like by default, because it makes sense, right? An LLM could have hallucination, and then a secondary or multiple agents can just course correct that. So it will be always better if we could get answers from multiple sources rather than just relying on one single source, in this case the source being an LLM agent. And again, now it with this kind of approach, you take away the human intervention part, where you don't really have to rely, I don't really have to keep on messaging, hey, you know what, the answer doesn't look right, this doesn't look correct, can you think about, or can you explain why? So these back and forth communications that we have, the agents can have again amongst themselves, just based on how you set up their personas, and then how you set up those chain of thought examples, right? How a math problem needs to be solved, a common sense reasoning problem needs to solve. So it should be extended to multiple such avenues, not just the ones that I've mentioned. So as part of the framework, we've kind of tried to have something built in such a way that yes, it could be extended into other fields of the AI space that we are currently in. Yeah, that's in a nutshell. That's all I have. I don't know if I was on time.
Hi, Sumit. Nice. That was a great talk and great session. And yes, you were perfectly on time. So thank you so much for this great talk. And yeah, so moving on, we're gonna have
Thank you.
an upcoming speaker, Eric Mells. Eric Mells will be taking us through enhancing LLM's intelligence with ARM, RAG, auxiliary rational memory for retrieval augmented generations. Eric Mills from Search Tax. How are you, Eric?
I'm good. Thanks. Thanks for that intro.
Great. Thank you. So now Eric Mills will take you through his journey with Search Tax. The stage is yours.
Thanks. So I'm Eric Meltz. I'm a Senior Director of Engineering at SearchStax. And today I'm going to be talking about enhancing LLM intelligence with ARMRAG. So ARMRAG stands for Auxiliary Rationale Memory for Retrieval Augmented Generation. Here's an overview of the talk. First, I'm going to present the fundamental problem we're trying to solve. Next, I'll present our hypothesis for solving the problem. I'll present some related work. Then I'll present the details of the ARMRAG system. I'll describe some experiments using the system, and I'll conclude with some final thoughts. So what's the problem? So the problem is bare LLMs are smart but forgetful. When you think about it, once a model is trained, its reasoning capabilities don't improve with usage. There's no explicit memory. All of the LLM's knowledge is frozen in its parameters. And since there's no modification of model parameters, the model's ability will not improve over time. So our hypothesis is that retrieval augmented generation, otherwise known as RAG, can be leveraged to improve reasoning performance over time. To apply RAG to reasoning, we'll take two steps. First, we'll store successful reasoning chains, otherwise known as rationales. And next, we'll retrieve relevant rationales when solving new problems. So there have been a lot of attempts to improve the problem-solving performance of LLMs. Some of them are just to build bigger models. So for example, GPT evolution shows that we get better every iteration. GPT-4 is much better at solving problems than GPT-3. Another approach is to fine-tune LLMs with rationales, and this has been shown to have success in certain situations. Another approach is to use RAG on question answering, and it's been shown that RAG can actually answer questions even when the answer isn't explicit in the context provided. So the drawback of the first two approaches is that it's incredibly expensive to train and fine-tune models. You need a lot of data and a lot of compute. And I think a previous speaker mentioned that it costs like millions of dollars to develop one of these LLMs. And RAG has typically been used in informational retrieval context and not in problem-solving context. So here's how the ARM-RAG system works. Using an LLM, we solve math problems. A product of solving math problems is we generate chains of thought, which we call rationales, and solutions. We save the rationales and the solutions into a knowledge base. And then when we're solving new problems, we apply RAG using the KB to improve performance on new problems. Here's some of the details. So the model we use for our experiments is GPT 3.5 Turbo from OpenAI. The retrieval model is Pyserini, which under the hood uses Facebook Research's Face Dense Vector Index. The data is the GSM-8K dataset, which was actually mentioned in the previous talk. It's a dataset of grade school math word problems with about 8,000 problems. And in our particular version, which was a little bit cleaned up from the original, had 5,000 training examples and 2,473 test examples. So here's a question from the data set that's going to be the focus of our first 3 experiments. So the question is, Josh decides to try flipping a house. He buys a house for $80,000 and then puts in $50,000 in repairs. This increased the value of the house by 150%. How much profit did he make? So GPT has some randomness depending on the temperature settings, and sometimes it'll answer the question correctly, and sometimes it'll answer incorrectly. So here we have examples of both a correct answer and an incorrect answer. Now, if you look at the incorrect answer, it goes awry in step 2, where it makes a mistake assuming that the value of repairs should be included in the original value of the house. And this mistake is propagated through the whole chain of thought and results in an incorrect answer. So in our first experiment, we just wanted to see on this one question, how accurate is it? So what we did was we prompted GPT 100 times with that question, and then we recorded whether the question was answered correctly or incorrectly, and computed the accuracy, which is just the number of correct responses divided by the total attempts. And the number that was generated is 34. So 34% of the time, GPT answers that question correctly. Next, in order to evaluate the potential effect of RAG, we wanted to investigate whether providing rationales as context could possibly influence the model performance. So what we did is we prompted GPT 100 times, like last time, with a question, but this time we also provided 5 correct reasoning chains for context that were, generated from the previous experiment. And this time we got an accuracy of 80%, and that's 46% greater in terms of absolute percentage points from the 34% baseline, which represents 135% improvement in performance. So this is a pretty dramatic, a demonstration that RAG can actually improve problem-solving performance if you get the context right, if you're retrieving relevant examples. Here, we're supplying the context by hand, but the hope is that RAG can have similar impact. So the next experiment, we went in the opposite direction, and instead of providing 5 correct reasoning chains for each question, we provided 5 incorrect reasoning chains. And oddly enough, the accuracy improved from the baseline. So instead of incorrect reasoning having a bad effect, it actually had a good effect. So it was up 5% from 34%, or a relative improvement of 15%. And it's a little mysterious why incorrect reasoning chains would help. But one possible explanation is that there's enough positive information in the context provided by the various chains of thought that overwhelm the minor mistakes that are there. So GPT may be able to sort of, take the good and minimize the bad. So in this next experiment, we shift our focus from a single question to the entire training set. So here we prompt GPT with each question in the training set exactly once. And when we do that, we see an accuracy of 73.2%. So recall from our case study that GPT doesn't always answer questions correctly. Sometimes it does, sometimes it doesn't. So to test whether GPT was capable of generating correct answers for the missed questions, we asked the questions multiple times and observed whether a correct answer was generated. So in this experiment, we prompted GPT with each question in the training set 5 times per question. And if GPT generated any correct answers, we labeled the question as answered correctly. And in this experiment, accuracy was 91.9%, which is a 26% relative improvement over the baseline. And this shows that GPT is pretty good at answering problems if you give it many chances. So in this experiment, we're employing our ARMRAG system. So let me describe the details. From the training set, we index questions and correct rationales into our vector store. And then for each new question, we construct a RAG context by retrieving questions and rationales that are similar to the target question. And we measure our accuracy on both the training and test sets. So this experiment yielded a 22% improvement if you're testing on the training set, and a 3% improvement if you're testing on the test set, meaning that these questions have not been seen and they are not present in the KB. So a 3% improvement is okay, but it's not as dramatic as some of the more focused experiments we saw earlier. So to investigate what's going on, here's an example of some documents that a target question retrieved. So if you notice, the target question is a story about a person going to a grocery store and buying various food items. And all of the retrieved results are also stories about going to grocery stores and buying food. But these questions structurally do not resemble the target question, in that the target question is actually adding up all the amounts and then performing a discount. And none of these retrieve questions sort of have that structure. So this shows that our retrieval technique is using surface similarity rather than structural similarity. So none of the retrieved examples conform to the type of problem this is, which is basically a discount of sums. So in the next experiment, we address this by attempting to dilute the effect of surface similarity by obfuscating the questions and the rationales. And we do this by replacing the objects in the problem by nonsense words. So here's an example. So this approach had a positive effect, resulting in a 6% relative improvement over the baseline. And doing a deep dive on this, you can see some of the retrieved questions when the target question is the obfuscated question. And you still see stories about shopping, but it's not all about food. So for example, in this example, you see mentions of coloring books and stuffed animals. So less emphasis on food, but it still might be a little bit more than we would like. So here's a summary of the results. Our baseline accuracy is 73.2%. With ARMRAG, we bump it up to 75.3%. And with the obfuscated ARMRAG, we get a performance of 77.4%, representing a 6% relative improvement. So some final thoughts. One, ARMRAG does improve problem-solving performance, and obfuscation helps improve performance even more. Our strong prompting experiment was pretty interesting, and it suggests that more gains are possible if we continue in this direction and can somehow retrieve highly relevant rationales. Here's some ideas for future work. We can employ more aggressive obfuscations. For example, maybe disallow non-math words. We can classify questions based on problem types, maybe label something as a discount of sum type question, for example. And perhaps we can induce more detailed reasoning chains, which may also improve accuracy. And that's the end of my talk. Thanks for listening.
Thank you so much, Eric. Thank you for this amazing session. And yeah, it was very fruitful and insightful. And upcoming next, we have our speaker, Gary Wolf. Gary will be taking us through the concept of SP multiple alignment as the double helix of intelligence. Gary Wolf, coming from Cognition Research. Thank you so much for joining us today, Gary. And the stage is yours. Gary, we can't see or hear you. Hello, Gary. Gary. I can't hear him or see him.
Can you hear me now?
Yes, now we can hear you and we can see you perfectly. Thank you, Gary. The stage is yours.
Okay, sorry about that.
It's okay.
Okay, well, I put up in this heading a word or expression which is probably not familiar to people. I'll be trying to explain it briefly. But I want to say a little bit about strategy. There's a very common assumption in work on artificial intelligence that people say, well, this is a really, really hard problem. So what we'll do is we'll tackle a corner of it, and then we'll try to work from there and get to what the real thing. And it's been tried and tried and tried. I'm not quite ready for my next slide yet. It's been tried and tried and tried for many, many years, and it constantly fails. I think that's a fair assessment. And so there's a school of thought that says if you're trying to tackle something big and complicated, you've got to have a broader approach and try to find a framework that will accommodate all the different sides of the problem. And to say I could go on for ages about this, but basically for a good many years I've been trying to do this, and the outcome has been this concept which I'll try to explain. Okay, next slide, thank you. The concept of SP multiple alignment is part of a general theory of intelligence, and this slide shows the overall framework for the SP theory of intelligence. It's a schematic of someone's head, and it's like a person's head. It's got information coming in through the eyes and ears and other senses, and I've labeled that new. So that's a technical term, new with a capital N. And the general idea is that the new information, the raw information, is compressed, and then you store it in your head. And the whole argument of this approach to intelligence is to say that it's every part of it is about compressing information, and it's not just an idea that's been plucked out of nowhere. There's actually a lot of evidence that brains and nervous systems do this, that it's a major part of how brains and nervous systems work. I could go on again for a long time about this, but I'll just leave it there. That's the framework, that it's about compressing raw information to make old information, which is stored. And if you can give me the next slide, please. Thank you. So it's a breadth first research strategy, and the overall aim has been to create or discover a theoretical framework with a computer model, embodied in a computer model, that could model diverse aspects of intelligence. In other words, you don't attack one small corner of the subject. You attempt to get a framework which will handle all different sides of the subject, and it's not easy. I've spent many years on this work. Now, the SP multiple alignment concept is the product of more than 20 years research, and I'm claiming that it's largely meets that objective of being a framework that can be then rounded out to understand the full complexity of intelligence. Next slide, please. Next slide, please. Okay. This is illustrating one stage in the process of discovering SP multiple alignment. And I won't give all the details, but at some stage, I realized that biochemists were doing something which was interesting, and they call it multiple sequence alignment. It's a technique used by biochemists for analyzing DNA sequences and sequences of amino acid residues. And there's an example in the middle of the slide. It's got 5 DNA sequences, and what happened is that they've laid them side by side, and then in a computer they've done a sort of let's stretch different sequences in order to find as many hits as possible, as many matches as possible between one sequence and another. And this result here on the slide is meant to be one of the better results that they obtained in with one of these programs that they developed. So I've said in multiple sequence alignment, 2 or more DNA sequences or sequences of amino acid residues are laid out alongside each other, and then in a computer, they are stretched to try and get the greatest number of matches between symbols from one sequence to another. Now, when I was looking at this, I thought, this doesn't do too badly on the compression front. We're looking for something that does a lot of compression. Well, if you match a lot of symbols, you can get compression by just merging the symbols and the sequences of symbols that match each other. So it married quite nicely with the idea of compressing information in order to model intelligence. Next slide, please. Okay, I hope this is clear enough to see. This is an actual SP multiple alignment produced by one of my computer programs, or the main one, which I call the SP computer model. If you can see, the top line is a sentence, and it says the plums are ripe. And that's, if you remember the second slide I showed, where we had new information and old information. Well, that top row, which is the 0 row, is called new information. So you imagine that comes in as new information, and then the system looks in its store of old information to try and make sense of it. So all the other rows, which are rows 1 to 8, are each one has a pattern from its store of old information. And as I say, it looks for things that match the new information. And you can see that THE in the sentence matches a stored record of THE. Plum matches a store of plum. There's an S, not S. We have the verb are, and then we have ripe. And the general rule is that when the program is looking to find these matches between old information and new information, it does a measure. It makes a measure of how much compression can be achieved. In other words, how much can you compress this new information by matching it up with the old information? And I think you can see that you don't have you can work out a condensed code because these things match each other. You can say, well, that means we can save on storing information. I'm sorry, I'm garbling this, but you can work out a compressed code for the new information, and then you can store that. So what have I said here? In an SP multiple alignment, row 0 contains new information. I put that in green and red. It contains an SP pattern, which is a sentence, and each of the other rows contains one old SP pattern drawn from a store of old SP patterns. And the SP computer model is designed to build one or more SP multiple alignments, in which the new pattern can be encoded economically in terms of the old patterns. Next slide, please. Next slide, please. Thank you. So is this any good for AI? Well, I'm claiming that it is. And I put some of the intelligence-related strengths of the SP multiple alignment concept. Now, on this slide, it's rather general strengths. I've said there's much evidence for the importance of information compression, I see, in learning, perception, and thinking in people and other animals. Now, the multiple alignment model or system, it's doing that compression very nicely. I've said SP multiple alignment is a powerful and versatile means of compressing information. It can be shown that SP multiple alignment is in effect an integration of 6 simpler forms of IC. And then in general, SP multiple alignment is largely responsible for the intelligence-related strengths of the SP theory. So I'll show you some of that in the next slide, please. Thank you. So more specifically, some of the intelligence-related strengths of this concept in natural language processing. It's not just natural language in general. It's particular aspects of natural language. It models classes and subclasses and parts and subparts in syntax and semantics. This is a prominent feature of the way linguists analyze language. It models the integration of syntax and semantics. It models discontinuous dependencies in syntaxes. This is where one structure leaps over another structure. I won't go into detail here. It models recursive structures in syntax, and it provides one framework for both the interpretation and the production of natural language. In recognition and retrieval, it models them as in terms of partial matches. It models classes and subclasses and parts and subparts in recognition. Recognition despite errors in the input data. semantic kinds of information retrieval, and various aspects of computer vision. Next slide, please. A few more things here, very much in outline. You can model, when I say planning, are things like finding one or more routes between two cities in a route planning exercise. You can do this with the model. You can do problem solving. These it kind, the kind of little puzzles that you have in IQ tests. Well, it'll solve those kinds of puzzles, providing they're in the form of sequences of symbols. It's got quite a long way in unsupervised learning, but there's more to be done there. And it models several kinds of probabilistic reasoning. I won't list them all. One-step deductive reasoning, abductive reasoning, and non-monotonic reasoning, and so on. And a key point, which I think is important, it allows these different things to be seamlessly integrated in parts and wholes, and that's that kind of seamless integration. I'm saying is an essential element of artificial general intelligence. Next slide, please. Finally, I'm going to stick my name out and put these claims forward. The SP multiple alignment concept has the potential to be as significant for an understanding of intelligence as is DNA for an understanding of biology. I know it's a strong claim. I think it's justified. So in more briefly, the SP multiple alignment concept could be proved to be the double helix of intelligence. Thank you very much. That's all apart from the last slide, which has a few details on. Next slide, please. All right. If you want more information, there's a website. The slides you can download via that tiny URL. There's papers about the research in that one. There's an email for me, phone call for me, and that's it.
Thank you so much, Gary Wolf, for this amazing presentation, an amazing session. And thank you to all our listeners for this session today we had. As we bring our Spotlight research session to a close, we extend our sincere gratitude to our esteemed speakers and for their insightful presentations. We're going to start with Eric Millis. We had Gary Wolf, Steve Phillip, Ayush Kashul, Kaito Song, Thurston Handler, and Nishant Gurav. You guys have shed lights into the forefront of AI research, inspiring us with innovative approaches. Let us carry forward with our spirit of innovation and collaboration as we continue to explore the possibilities of artificial intelligence with our upcoming session, Agent-Based Systems Paper Presentations. Thank you all for your participations and organizers for making this session a success. So we will be back shortly after a short break, and we'll come back with Agent-Based System Paper Presentation. Thank you, and see you all after the break. Have a nice day.